All right. Are you able to see my screen?
Yes.
Yeah. All right. Hello, everybody. Hope you are doing good. Greetings to everybody. Good evening. To all the people who come from around the world, we are extremely happy you are here. On behalf of Propagation Institute of Advanced Studies and SA Citizen Science Group, I'm delighted to welcome all of you to World Space Week, the largest global celebration of space and science. This year's theme is Life in Space. So we will do a bunch of topics ranging from how satellite navigation systems work to how life in space goes, which will be taught by Molika Karmam. That's very nice. I'll tell you a few things about myself. I am Yesh, one of the people here at Propagation. At Propagation Institute of Advanced Studies, we bridge the gap between the learners and the people who are extremely scientific and have done a great amount of work there. We are trying to build one of the largest communities of researchers, scientists, learners, all together at one place to come together and work on their fields. All right. We have a collaboration today. We, like always, with SA Citizen Science Group, headed by Soban Acharya sir. It is one of the largest citizen science groups in India, where if you wish to contribute anything to science, that's the place to go because it's completely awesome. People are extremely helpful. This is the place to go there. All right. Now, about why we are here today. We are here today celebrating World Space Week. From October 4th to 10th, we will host 7 interactive sessions, each featuring leading scientists and researchers who will help you out in a bunch of topics that are extremely interesting and worthwhile watching. All right. All active participants will get their certificates after 10 if you have attended all 7 sessions and have done interacted with the people. All right. Now, I am extremely delighted I am introducing Amitava Gupta sir. He's a huge inspiration, a very fantastic personality. He will be taking the topic on navigating the world, the science behind satellite navigation. To tell you a few of his credentials, he's a distinguished professor, Department of Space at ISRO, ex-chief scientist, CSIR. So you can be sure that you will get the best of the knowledge there is. All right. A few instructions for you. All the questions will be taken at the end of the session. If you have any questions, you can type them out on the chat. They will be taken at the end of the session. All right. Keep your ears open. And when you have questions, you can type them out, but we'll take them at the end. So you can take the mic now. The introduction is good. We will take on to the main topics from here. I'll stop presenting. And so we'll speak now.
Great. Would you like me to share my screen now?
Yes, sir. Yes, sir. We can, please.
Okay. Can you see my screen?
Yes, sir. We can.
Great. Thank you very much for that kind introduction. I am going to spend the next 45 minutes to an hour talking about this very interesting topic, navigating the world, the science behind satellite navigation. I must warn you that this talk is at a very elementary level. So most of you, perhaps some of you are already aware of what I'm going to describe, but this is for a very broad spectrum audience. Those of you who are not familiar with the satellite navigation, the details of it, will probably benefit with this story that I'm going to tell you. So I also would like to say in the beginning that I'm not going to use a lot of mathematics, graph, results, charts, etc. It's mostly pictorial, just an elementary description of what is behind navigation and specifically satellite navigation. Now, there are 2 things that we take for granted today. These 2 things is what is our location. You want to know where you are on the Earth. You know it within a few meters. And what is the time? So anytime you want to know your location, you just take out your mobile phone and use Google Maps, and there you are in this, right? Can you see my pointer on the screen?
Yes, sir, you can.
Okay. Okay. So you can see where you are with respect to the city map and so on. And also you have the time display on the mobile phone. This is very accurate time, which is synchronized. The server of the internet service provider synchronizes it with the satellite navigation system. So these are the two things with them. And when we are out on the roads, unfamiliar road, we turn on the GPS receiver, and on the map, it tells you exactly which road you must take and how you should navigate your way through the traffic. And the aircraft, when it's coming in to land, the pilot just gently sits inside the cockpit. And you notice that he doesn't have to make a lot of effort. He just effortlessly knows exactly where he has to land. And there he goes. So it's a very simple operation. It's called fly-by-wire aviation. And then you have these precisely guided missiles. In the warfare, you hit targets which are thousands of kilometers away, and you just, sorry. And the missile just takes off, and it's precisely guided to the target, which is a couple of thousand kilometers away within a few meters, and it hits it. So the precise, reliable, and automated navigation called PNT, position, navigation, and timing, has become such an integral part of our everyday lives that we often take them for granted, particularly the young people of your generation probably think that, hey, what is so great about it? It should be there. So you just take it for granted. But perhaps sometime, some of you at least, you wonder how it all works. What is the science behind? What is the intricate engineering behind this whole thing? So in this story, we are going to tell you in very, simple details, the details of the satellite navigation. I start with the understanding of basic concept of navigation. I just give an oversimplified picture, very simple picture. Supposing you are an unknown, you are in the middle of the city of Delhi, you don't know where you are, you're just lost. So let us say that at three corners of the city, we have three towers. On this corner, left top, we have the Rohini Pitampura TV tower. We have Qutub Minar here in the left, and we have the Unitech tower in the east part of Delhi. Let us say these are very tall towers, and on top of each one of these towers, I put a transmitter, a strong transmitter each, and I also put a clock on these transmitters and transmit a periodic time signal. Every 5 seconds, it just sends a time signal. So let us say this user or you have a small receiver which has a clock inside and which can receive this periodic time signal and finds out what time this signal arrived, right? You know when the signal was transmitted. Your receiver here tells you what time this time signal was received, and hence you know what was the time it took to travel this distance from this Pitampura TV tower to you, right? Let us say, just for argument's sake, and you know this signal travels with the speed of light because it's a radio signal, and so you multiply this time taken to travel times the speed of light, so you get the distance. Let us say it turns out that your distance is 19 kilometers from the TV tower. That doesn't tell you very much, except that with Pitampura tower as the center and 19 kilometers as the radius, if you draw an arc, you can be anywhere on this arc, right? This is what it tells you, this measurement. Now, suppose you turn your attention to the other tower in the eastern part of Delhi, and you do a similar exercise. You receive that time signal, find out how long it took to arrive to your location, multiply that with the speed of light. You know the distance. Let us say you find out that distance is 12.5 kilometers. So then you can draw one more arc with this as the center and 12.5 kilometers is the radius. So where these two arcs intersect, one here and one there, are the two possible places where you can be. But it's still not unique. So then you turn your attention to the third transmitter, which is Qutub Minar, and let us say you find out that you are at a distance of 15 kilometers from there. So you can draw a third arc, and the place where these three arcs with these three transmitters at the center intersects, that is the place where you are. So this is the way the navigation works. You have to have at least three transmitters, each transmitting a time signal. And these time signals, all the clocks at these towers must be precisely synchronized with each other. I'll tell you later why they should be synchronized. And then you have a clock inside your receiver, and you find out how long the signal took to travel from the respective transmitter to you. And then you draw these arcs, and where they intersect is where you are. So this, friends, is a simple principle on which the navigation is based. This is called the principle of range navigation, right? Now, suppose you say that, hey, I don't want to be just confined to the city of Delhi. I want to be anywhere on the earth, global navigation. I want to be anywhere on the earth. So if you want to be anywhere on the earth, hey, what happened? What happened? So if you want to be anywhere on the earth, then you must put up these transmitters with synchronized clocks, and you have to use millions of such transmitters to cover the entire globe, and which is not a very practical idea, because there are places which are inaccessible. You have oceans, you have mountains, and all kinds of inaccessible places. So the way in which you can alleviate such situation is satellite based. If you use satellites, the satellites orbit the Earth. Something is happening. Let me just unshare the screen and start it again. Okay, just 1 second. I have to share it one more time. Can you see my screen now?
Yes, sir.
Okay, there you go. Okay, so you have these satellites which are orbiting the Earth at very high altitudes, and you can have a number of these satellites. And instead of those three transmitters that I talked about at the three corners of the city, you can use these satellites as transmitters. On board each satellite, you put a clock and a transmitter, and then you can have these satellites mimic what we just described earlier for the city of Delhi, right? Now, you are a user on the Earth, and you don't know where your location is. You turn your attention to one of the satellites, find out with respect to this little clock that you have in your receiver, how much is the time taken by this signal from the satellite 1 to travel to you. And then you draw one arc, then you turn your attention to the other satellite, draw one more arc, you turn your attention to the third satellite, draw one more arc, and then you know where your location is. This is the way, and these satellites, because they are orbiting the Earth at very high altitudes, they can cover large portions of the globe. And because they're moving around, they can effectively, provided there are sufficiently large number of satellites, you can cover, with this navigation system, cover the entire globe, including the oceans and the mountains and inaccessible areas, right? Let us do a little bit of a mathematics. I promise I won't do much mathematics, but just a little bit of mathematics. What does the receiver measure? The receiver is measuring the time difference between the time which was transmitted by the satellite and the local clock. the time between the clock and the received signal. And let us say that time is tau, right? The time at the transmitter, at the time at the receiver. Now, if you multiply, I said, because this is a radio signal which travels with the speed of light, if you multiply this time difference with the speed of light, c, you get the distance or the range. Now, this range, let us say the satellite is here and the coordinates of the satellite are in Cartesian coordinates, x1, y1, z1, and the coordinates, unknown coordinates of the receiver are xu, yu, and zu. And what is the simple formula for range? It is given by r1, the distance to the satellite 1 is square root of x1 minus xu whole squared, and so on. So this is a very simple expression that all of you know. Now, unfortunately, what we measure is not this distance. You know why? Because the clock on the receiver, this is a very cheap receiver, and when you start the operation, this clock is not synchronized to the clock on the satellite. So there is a little difference in the time of this clock and the clock on the satellite. So what we measure is this expression. This is the range minus a small error term, which is the time difference between the clock on the satellite and clock on the receiver, clock on the ground, right? You must have a correction term, c times delta t. And we call this not the range, but the pseudo range, because this is a range with a little correction. Now, you can get, depending on which satellite you are receiving the signal from, you can get the pseudo range from the satellite 1, which is this expression, satellite 2, satellite 3, satellite 4, and so on. Now you see in all these equations, x1, y1, z1, the satellite coordinates 1 of the first satellite, coordinates x2, y2, z2 of the second satellite, and so on. These coordinates, we presume that are known because the satellites are traveling on precisely known orbits, and we know exactly what their coordinates at each instant of time is, right? So the only unknowns here are the user's position coordinates, xu, yu, and zu, and the error of the receiver's time, right? So there are 4 equations and 4 unknowns. So if you solve this set of simultaneous equations, you can solve for these 4 equations. So 4 simultaneous equations and 4 unknowns. So you can uniquely solve the unknown coordinate. This is the basic mathematics behind the satellite navigation system. So what is required? A few salient points. The satellite requirement is that each satellite must broadcast a time signal, and each satellite must also tell the user what its position is, x1, y1, z1, x2, y2, z2. These position coordinates of the satellite, positions of the transmitters, must be told to the receiver, right? And what is the requirement of the receiver? The receiver must be able to receive the signal from multiple satellites simultaneously and determine the ranges. Yeah. So that's how you get 4 simultaneous equations. You must be able to simultaneously receive signals from multiple satellites. And then you must have in the receiver a small computer which gets these pseudo ranges, and then using these 4 simultaneous equations, it's able to do some calculations. So there must be a powerful enough computer inside this receiver which is able to solve 4 or more simultaneous equations and give you the user's coordinates and the time, right? And there is an important requirement here. What is that important requirement? The clocks, as I said before, the clocks on board all the satellites must be very accurately synchronized with each other. Let's see why this is so. See, in these set of simultaneous equations, I said the 4 unknowns are xu, yu, zu, and delta t. Now, this delta T, you see, appears in all equations. That is because the time of all the satellites is the same. So the difference between any satellite and the receiver is just delta T. It's not delta T1 for the satellite 1, delta T2 for satellite 2. That would be if each satellite transmitted at different time. Because all the satellites are synchronized with each other, you have one single term, delta T, which appears in all the equations. So that's how you have 4 equations and 4 unknowns. If the satellite clocks were not synchronized, you'd have more unknowns here, delta T1, delta T, etc., and you couldn't solve them, right? So that's why that is a very important requirement, that all satellites must transmit identical time. The clocks on board all satellites must be precisely synchronized. Now, you cannot, because these are objects which are very far away, clocks are different, you cannot have perfect synchronization. So let us just estimate how precisely the satellite clocks should be synchronized with each other for this assumption that delta T is equal in all the equations to work. Yeah? How precisely should the satellite clocks be synchronized? You realize that the signal is traveling with a very high speed. It takes only 1 microsecond to travel about 300 meters. The speed of light is 3 into 10 to the power 5 kilometers per second. So in 1 microsecond, the signal travels about 1/3 of a kilometer. So if the clocks have a synchronization error between each other of just 1 microsecond, it turns out, I can show you in the set of equations, that if there is a synchronization error between the satellites of just 1 microsecond, then the position that you calculate by solving these simultaneous equations is about 1 kilometer or so, which is terrible. You don't want 1 kilometer uncertainty of your position. So if you want navigation at the level of few meters, you must synchronize the clocks on board all the satellites to within a few nanoseconds or a few billionths of a second. Now, this is a fantastic requirement. This is a very difficult requirement and is possible only if you have all the clocks on the satellites as atomic clocks. I don't know if some of you attended my earlier talk about a couple of years ago on this forum on how an atomic clock works, but I'm going to talk details about that. So, another important requirement is each satellite must transmit its position. Now, you see, the satellites do not continuously broadcast their instantaneous position because that will be too much of information. No? At this position, it says I'm at X1, Y1, Z1. The next second, it says I'm at X. So that's a lot of information. So instead, what the satellites broadcast to the users is the shape of the orbit, and that is called orbital elements or satellite ephemeris. Please don't pay much attention to these technical terms, but I just wanted to say that the satellites must continuously broadcast their orbital information, right? Okay, now there are several different worldwide navigation systems. We are all familiar with GPS. GPS is something which is, which everyone knows. I mean, we call the satellite navigation system de facto by the name GPS. But GPS is a global positioning system, is an American defense satellite. It is a constellation of 31 satellites. But in addition, there is also the GLONASS, which is run by the Russians, a constellation of 24 satellites. Galileo, run by the European Union, a constellation of 27 satellites, a Chinese constellation called Beidou, 45 satellites. And then there are 2 regional satellite systems. One is the Quasi-Zenith Satellite System, QZSS, Japan, 4 satellites, and our own NAVIC system, or the Indian Regional Navigation Satellite System, is a constellation of 7 satellites at the moment. Now, I'll just take you now to understanding the overall architecture of the satellite navigation system. So let's just see the primary requirement of a satellite navigation system are the satellites, right? So you must have a constellation of satellites. Now, each satellite acts as a transmitter. And so on board each one of these satellites has to be a clock and some transmitter, some electronics, which transmits this time signal to the users down below on the Earth. So this and all these satellites must be orbiting the Earth at certain known orbits, right? So this entire system of all the satellites is called the space segment, right? Now, these satellites, they broadcast the time signals. They broadcast time signals that cover literally the whole Earth. Now, down below on the ground, we have some tracking stations. These are not the users. They are just the large antennas, large systems, which track the signal from the satellite. They are placed, their positions are very well known. So when they receive the signal from the satellite, they can actually work on the orbit of the satellite. They can also find out what is the error of the satellite clock, etc. So there's a network of these tracking stations, and these tracking stations send all their data to a master control system. I mean, I've shown only one tracking station, but there's a whole network of them spread over a large area, literally covering the whole world. And they collect the data from the satellite to determine their orbits precisely and to find out the errors in the clocks on board, right? And all that data gets collected at the master control station, and where the computations are made for the satellite orbits, and then and also the clock corrections. And then there's an uploading station which uploads these corrections to the satellite periodically. So that's how the orbit information on the satellites, the clocks on the satellites are all kept synchronized. So this entire system is called the ground station control segment. This is a very important section of the satellite navigation system. Then finally, the signals are received by the users, and the users are you with your mobile phone. Then there are GPS receivers on the vehicles. There are ships, aircrafts, and a lot of other users. This entire, and all the users must have receivers which are able to simultaneously receive signals from all these satellites in any specific constellation, have a computer that solves the simultaneous equation, determines the position, the way the receiver is moving, and so on, navigation, etc. So this is a multi-billion-dollar industry, namely making these receivers optimum, compact, and so on. So this is the user segment. So there are three segments: the space segment, the control segment, and the user segment. That's the overall satellite navigation system for you. Now, before we go on to other details, I just thought that I should show you, for some of you that are not familiar, how does an actual satellite look like? What does it typically look like? So this is an actual photograph of a GPS satellite. This is what it looks like. It is powered by batteries which are charged by large solar cells which are deployed, and they look towards the sun and produce enough power to run the satellite. And then there's the clock and the transmitter inside, and these are the antennas which look towards the Earth to transmit the signal. And you must be trying to, wondering how big this satellite is. And this satellite is typically this big. Look at the men here, and the solar cells are folded back on itself. They are deployed once it's up in the space. This is a GPS satellite, and it's very expensive, costs a few $100 million. So that's how expensive these things are, and fairly big. You can see with respect to these men that are standing here, there's a huge satellite. Okay, now while we are at it, I thought I'd show you one of our own satellites in ISRO. This is one of the Navik satellites. and look at the people, and that's how big the satellite is. And it costs a few hundred crores, about 300 to 400 crores. A very expensive business, this satellite navigation system. So, and I thought while we are at it, the next thing that I need to show you is these satellites are launched into the orbit, you know.
A new GPS satellite blasted off from Cape Canaveral, Florida. But Delta IV lifted off on Friday. Here it is. It's a navigational satellite. It'll provide the U.S. Air Force with improved military signals, they say. They have greater accuracy and are more resistant to signal jamming. It also has a longer life expectancy than the previous generation.
Okay. So what I just wanted to tell you was building the satellite, launching the satellite are all very difficult, very expensive, and highly technical endeavors. And these are some of the things that go behind making this satellite navigation system work. And they cost a few $100 million US dollars. I mean, that's how expensive this whole business is. And at the heart of this system, on board each one of these satellites are these unimpressive looking atomic clocks, which are very precise clocks, which would lose or gain 1 second in a few 100,000 years, right? I'm not going to tell you details about the atomic clock. Now, in addition to the atomic clock, which provides the time signal, there's also a lot of electronics, which is called the navigational payload. This converts the time signal into certain codes and then makes it ready for transmitting it down to the users on the ground, right? So now the next question we want to ask is, we said, okay, we must have a constellation of satellites which navigate, which go around the Earth. Now, the question that I would like to ask is, how should the navigation satellites orbit the Earth? You know, what kind of orbit? Now, you are all familiar with, for a global navigation system, the satellite should be visible to most points on the Earth during some part of its orbit. They must cover a wide area, right? At any given time, at least 4 or more satellites should be visible at the user's location. And each pass of the satellite must last for a reasonable long duration of few tens of minutes or longer, right? So these are some of the requirements of how I want to keep my satellites revolving around the Earth. Now, what should be the shape of the orbit, I ask myself. Well, you're all familiar that, there's Kepler's law. It says that if you launch a satellite and if it goes around the Earth, it must follow Kepler's law. And Kepler's law say that the satellite orbit is an elliptical orbit, right? Now, a special case of an ellipse is a circle. When the ellipticity is 1, it's a circle. So I want the satellite in a satellite navigation system not to have an elliptic orbit. I want it a circular orbit. So these orbits are as close to a circular orbit as possible, right? So that answers the question of what should be the shape of the orbit. Now, what should be the height of the satellite orbit above the Earth? So there are different categories. There are low Earth orbit satellites, or the LEO satellites, which are only a few 100 kilometers above the surface of the Earth. And these LEO satellites, they go around the Earth at only 400 to 1,000 kilometers. And if I have my satellite navigation satellites in LEO orbit, then unfortunately the coverage of each one of these satellites is very, very small. They don't cover a lot of space because they're very close to the Earth. If I have medium Earth orbits, which are slightly higher, 2,000 to 30,000 kilometers, then the coverage is slightly greater. I can also have them in high Earth orbit, and a special case of high Earth orbit is when the height is 36,000 kilometers. The time period is exactly 24 hours, that's the period of rotation of the Earth, and that is called a geostationary orbit. So we can have them in geostationary orbit, but then they will not cover a lot of portion of the globe. So the geostationary orbit, naturally, the coverage is very, very wide. It covers almost from pole to pole. Now, then the next question I ask is, what should be the inclination of the orbit? By inclination, I mean this. Let us say this is the Earth, and it's rotating about its axis, north-south axis, in this fashion. It's rotating once in 24 hours. Now, I can have a satellite orbit along the equator like this, right? This is called an equatorial orbit. The inclination of the orbit with respect to the equator is 0. But if I have an equatorial orbit, then the coverage is around the equator, mid-latitudes, but it does not cover the poles, right? I can also have the satellite orbit in a polar direction. This is called a polar orbit when the inclination is 90 degrees with respect to the equator. This is a polar orbit. If I have a polar orbit, then the coverage around the poles and mid-latitude, etc., is very good. But unfortunately, it doesn't. These kinds of orbits don't cover the equatorial regions. But a compromise is an inclined orbit like this. An inclined orbit, the advantage is it covers both the equators and the poles, right? So, I mean, we'd prefer to have a satellite orbit which is inclined to the Earth's equator at some angle of some 45 degrees or so, okay? So finally, the global navigation satellite orbits look like this. They are circular orbits. They are medium Earth orbits, around 20,000 kilometers. The orbital period turns out to be about 12 hours, and they are inclined to the orbit at about 45 to 55 degrees. So that's typically the kind of orbits that we have for the global navigation satellite systems, right? Okay. Now, the entire constellation, so this is just one satellite. We want to cover the entire world. So the entire constellation is called, don't worry, I'll explain this term with the help of a nice video. It's called a bird cage configuration. In a bird cage configuration, you have these inclined orbits, but in certain planes. So there are, as I said, the GPS has 31 satellites, and they are medium Earth orbits, 20,000 kilometers, inclined at about 55 degrees. And then the Galileo has around the same, around 23,000 kilometers, inclination 56, and so on. And GLONASS has this. But all this is not a very visual thing. So let me show you this picture. So this is how the GPS satellites are orbiting the Earth. So this is the Earth, and it's going round, rotating about its north-south axis. And each satellite, it's going round in an inclined orbit, in a circular orbit. And because there are so many of them in different planes, at any given point, you can receive at least 4, in fact, many more than 4 satellites, no matter where you are on the Earth. So this is about the orbits. Now, then the next question I asked is, what frequency should the satellites transmit? Now, you know that the sun, which provides our visible lights, makes day and night possible. It also transmits extreme ultraviolet and X-ray radiations, which are very harmful for us. And now, these harmful radiations, fortunately, are absorbed in the upper portions of the atmosphere, where they are absorbed and result in ionizing that portion of the atmosphere. This is called ionosphere. So ionosphere is at a height of 250 to 300 kilometers, consists of very highly ionized plasma here, right? One of the problems with this plasma is, if I have signals which are less than 25 megahertz, the VHF signals, they're reflected from the ionosphere. They don't penetrate the ionosphere. But my satellite is very far away. It's about 20,000 kilometers. So the signal that I transmit must have a frequency which is much more than this, right? So usually the frequency that we use is a microwave frequency called the L band, 1100 to 1600 megahertz. So the transmitted signal are typically about 1100 to 1600. So I'm not going to go into details of this, but just to tell you that the GPS constellation transmits two frequencies, 1.5 gigahertz and 1.2 gigahertz, right? So just quickly go through, don't worry about these details because you can't remember them, but all the constellation, GPS, GLONASS, Galileo, Beidou, IRNSS, QCSS, all the satellite constellation essentially transmit in the L band, 1.5 gigahertz, 1.2 gigahertz, and so on, right? Now, then the next question I ask is, how much power should the satellite transmit? I have a transmitter which is transmitting time signal. What should be the power of that transmitter? It turns out that you don't want to, ideally you'd like to have a strong transmitter so that the receivers can easily receive them. But then the problem is, because there are so many of these satellites, if you transmit a strong power, then the receivers will get saturated. So typically the transmitter power is only about 30 watts. Imagine a 30-watt transmitter, which is sitting at a distance of something like 20 to 25,000 kilometers away. So the signal and the antenna is beaming this signal only to cover the Earth. It has a radiation pattern which has a beam width of only about 28 degrees, which is sufficient to cover the Earth. You don't want to waste the transmitter power by radiating the signal all around, right? So the signal, that's why those antennas are looking directly to the satellite. So has a beam which is very accurately determined so that it covers only the Earth and a little bit beyond. So, and finally, this only little power, 30 watts or so, at a distance of 20,000 kilometers, when it reaches the Earth, it is a power of about 10 to the minus 16 watts, about 0.1 femtowatts. It's a fantastically low power. It's actually less than the noise level in the receivers. It's a very small power, so you need special efforts to receive these signals. And the next few slides I'll quickly go through because it may be somewhat technical for many of you. So what is the signal model? We said it transmits a satellite, all the satellites transmit a time signal, but these time signals must be coded by some modulation in a certain format. Now, please recall the main requirement is that the receiver should be able to simultaneously receive from several satellites to determine the pseudo ranges. Now, the signal frequency transmitted by all the satellites is the same. Each satellite must transmit a unique code. So hence the system is called Code Division Multiple Access, or CDMA. For those of you who are familiar with some communication jargon, so CDMA is the kind of modulation that the system uses. So, and also the actual code which is transmitted, which is called a pseudo-random noise code, PRN code. And I'll not go into details of why we use a pseudo-random code, except that it offers a lot of advantage, including ability to achieve very high precision ranging and detection and a lack of interference between two signals from two different satellites and so on and so forth. It provides a lot of interference and noise immunity. And I thought I'd give a little description of what is a pseudo-random noise code. For those of you who are familiar with some electronics, a pseudo-random code can be generated very simply using, D flip-flops. These are shift registers. These shift registers are connected in series. They're all clocked simultaneously, and we take feedback from some of the portions, and feed and XOR them and feed them back at the input of the first sequence. So if we do this, we get a sequence which on the face of it looks very random, but it repeats after a certain amount of time. So that's why it's called pseudo-random. So I more than that, I'm not going to tell you. The big nice property of these pseudo-random codes is that it offers very good cross-correlation. One code with respect to another code does not correlate at all. And the same code with respect to itself correlates only when it's perfectly overlapping, just one chip shift, and there is no correlation. So it provides a lot of noise immunity. Now, the code that we use is what is known as a gold code. Don't worry about the details. It's a class of pseudo-random codes which can be formed in a certain special way. So let's skip all that. So inside the electronics, the signal modulator, the electronics is very simple. It's like this. You have a sequence of shift registers, some fed back to they're all clocked identically. And then what it generates is a certain pseudo-random code. And then you have another code generator. This generates another code, PRN2. And if you can combine these two, what comes out is what is known as a gold code, when you have certain combinations of them. And you can change the phases of these to generate different gold codes. So each gold code is unique to each satellite. So you generate different gold codes, right? So this is the basic electronics that goes inside the signal modulator. And there are, of course, many more details, but let's skip all that, right? And remember, I showed you that navigation payload. This is the electronics that is there in that navigation payload, and some more things like what. Now, this is the basic modulation, right? The gold code. But there also has to be a lot of information. So there has to be a lot of data. And the data has to be formatted in a certain way. In very simple word, they're formatted into 30-bit words. These are matter of details. Don't worry about them. But all the data are finally compressed into a frame which is approximately about 12 minutes. In case of GPS, it varies a little bit for other constellations, but typically the entire data takes about 10 to 15 minutes to be transmitted, right? And what does the data consist of? Data consists of the satellite ephemeris. Remember, I said the satellite must broadcast its orbit information, satellite ephemeris. It must consist of clock corrections and almanac and the ionospheric model, etc. So all the data in one super frame, which is about 12 minutes, is the data which the receiver receives from the satellite. Now, what does the receiver look like? The receiver must have an antenna, and it must have an amplifier, a preamplifier, which is able to receive this extremely small signal. The signal is about 0.1 femtowatts. So this has to be extremely low noise signal. So it amplifies this signal, converts it, demodulates it, and then finally, this signal processing unit is the one that is able to find out the time delay. There is a clock inside the receiver, and with respect to that clock, the received signal, how much is the delay, the pseudo range, the rate of change of pseudo range, and all the navigation data, namely the clock correction and the satellite ephemeris, etc., are all available at the end of the signal processing. And this application processing is that little computer that I talked about. Once the pseudo ranges are available from multiple satellites, minimum 4 satellites, it can solve simultaneous equations and provide you position, velocity, time, etc. So this is how broadly the GPS receiver works, or the GNSS receiver. And the antenna look typically like this. Sometimes they are much smaller. I'll show you much smaller antennas later on. So the signal processing in the GPS receiver consists of splitting the signal. Never mind. The first point, basically what I'm trying to say is, all the signals are received at the antenna. All the signals from all satellites are received at the antenna simultaneously. So what you receive in the receiver, what you receive here is a jumble up of the signals coming from all satellites, right? Now, you must, in the signal processing, you must have different channels for finding out the signal from each satellite by doing correlation, right? So the signal must be split into multiple channels for signal processing and finding out the pseudo ranges. And then you acquire the satellite, you track the code and demodulate the data from the satellite. So I'm just skipping through this because this is a lot of information which is not really necessary. You know how the receiver works. And what is the output of the signal processing? As I said, you get the pseudo range from each satellite. You get all the data, the clock corrections, the satellite orbit information, etc. And then there is that little computer which is able to use this data to calculate, do navigation, and solve simultaneous equations and give you the position. It also can give you the delta T and hence give you the time of the day exactly. It also tells you ionospheric data, which I'm going to tell you later on. So a little bit of detail about GPS receiver, the receiver evolution. Now, unlike many of you, I happen to be from very ancient times. When I was roughly your age, this was 1980s, and that's when all these GPS systems had just started working. So this is the kind of receiver that we used to use. I mean, around 1979, this is a huge receiver which used to receive signals from the satellite, right? And over the years, there have been some evolution. In the 90s and 1970s, it used to be one rack full of instruments, you know. And then came the Gulf War. The Iran and the American military used to carry these huge GPS receivers, 1980. And then the receivers, early civilian survey grade receivers, became somewhat smaller. And then they became portable, not yet very portable. 1990s, GPS became fully operational. And then compact receivers started getting available in the market. I remember around 2000, 2001 or so, I had purchased myself a small receiver costing a few $100s, which used to tell me where I am, you know. So, but it was still very big. Now then came these personal navigation devices, and first time around 2008 or so, the GPS cell phone in satellite navigation receivers in cell phones started becoming available. And today, of course, all the smartphones have GPS, which is built in. Now, how is it possible to have such a huge system? It's a very complex system, right? Amplifying that very minute signal, splitting into multiple channels, acquiring the signal, doing the computation. It's a lot of activity. So what exactly has happened that has made this transition from huge receivers to very tiny receivers? So see, the receiver basically is required to receive signals from multiple satellites simultaneously and determine the ranges. And it must have a small computer that is able to simultaneously solve simultaneous equations in real time, right? So these are the requirements. So the generic receiver, which I showed you earlier, has this all analog processing of this signal, and here there are multiple channels for signal processing, one channel for one satellite. So if you are receiving signals from 27 satellites, you must have 27 such units here. So that makes it very large, right? But today what we do is we have digitized. What one does is one amplifies this precise signal, it down converts it, and then you convert it into digital form, analog to digital computer. Once you have a series of digits, zeros and ones, then you can use digital signal processing, which can be done in very small receivers, very small electronics. So the hardware, basic hardware reduction has come here. And also the power of these application processing chips, that has improved enormously over the last few tens of years. So this is what has resulted in significant, reduction in the size of the receivers. Today we have receivers, sometimes you wonder, where is the GPS receiver in your mobile phone? So this is where it is. In your mobile phone, you have multiple layers, and the GPS antenna is a little printed circuit on one end of one of the boards. So this is a printed circuit antenna. This is how miniature the whole thing is. And there are only two chips. So this chip here is the one that amplifies that tiny signal from the antenna and does A to D conversion. And this baseband processor is the one that does the signal acquiring and all computations, etc. Just these two chips constitutes the entire navigation system in a typical mobile phone. Right. Now, I'll spend, do I have some more time?
Yes, sir. Yes, sir. You do.
Okay. Thank you. So now I'll talk about a little bit more about the system, a little more details. Now you have the basic, know the basics of how the whole thing works. Let's talk about position uncertainty. So we said that you are somewhere on the Earth and you receive signals from at least 3 or 4 satellites, and you draw these arcs, and where the arcs intersect is your position, right? Now, in real life, and this is where your position is. But in real life, what happens is these pseudo-range measurements are physical measurements, and they are not exact. There is a little bit of uncertainty in that measurement, error in these measurements, because of which these lines are not just lines, they're bands actually. This line is a certain band, this red line is a certain band, and so on. So now when you solve a simultaneous equation with uncertainty in these pseudo-range measurements, where you get a convergence in the simultaneous equation solution is not one point, but a region. So this leads to an uncertainty in the position determination. So your position could be anywhere in this shaded region. So this is a simple illustration of how we get uncertainty in our position determination because of errors in the pseudo-range measurements. Now, let us go back to those early equations that we showed you, and we said that there is a correction term, the real range, and a small correction term, c times delta t. And we very conveniently assumed, to simplify matters, that this is an electromagnetic signal and travels with the speed of light c. But the fact is that it would travel with speed c only if the intervening medium had been perfect vacuum. Unfortunately, it isn't. It is in vacuum, and hence the light does not travel with the speed c. There is a little difference. Now, so you must add these correction terms. There is the ionosphere in between, which is ionized. So when the signal travels through the ionosphere, it's slightly slowed down. So there is a little extra delay because of the ionospheric propagation. The troposphere, which is close to the Earth, first 10 or 15 kilometers, also slows down the signal a little bit. This is the tropospheric delay. Plus there is receiver noise, multipath, etc. I'm not going into details. So these are some of the sources of errors in the pseudo-range measurement. So ideally, I should have traveled with the speed of light in vacuum, but in real life, there are these error terms which come in, because of which it doesn't become a line, it becomes a band, right? Now, because of these ionosphere, troposphere, and the receiver uncertainty, multipath, etc., so let us see what kind of errors typically happen. Now, the typically contributing sources for the uncertainty are the following. The satellite clocks. On board each satellite is a clock, which is, one tries very hard to keep them all synchronized, but still there are some uncertainties, because of which we get a pseudo-range uncertainty of a couple of meters, 2 meters or so. The satellite orbits, we want to determine the orbits very, very precisely, but still the orbits are not so precise, because of which we get some error in the pseudo-range, typically plus or minus 2.5 meters. The ionosphere delays the signal a little bit. This is the largest source of uncertainty, plus or minus 5 meters, the troposphere a little bit, and so on. So finally, when you can add up all these things, the RMS uncertainty, typically in a satellite navigation system, is about 5 to 6 meters, or sometimes even 10 meters, depending on where you are. So as a result, when I use the GPS receiver, I get a position which is not a fixed point, but it is an uncertain region, which is about a few meters diameter, right? It is uncertain. Now, for some applications, for most applications, this is just fine. When I'm traveling on the roads of Delhi with my GPS receiver in my car, I really don't care if I'm here or 2 meters this way or that way. It really doesn't matter. But there are applications where I'd like to know my position very, very precisely to within a few centimeters, or at least to better than 1 meter. So what do? We have a method of improving the position. That is, I'm not going to go into great details, but tell you just the basic principle of what is known as differential GNSS, differential GPS. What do we do here? Very simply, supposing you have a receiver and you receive signals from multiple satellites and do this position solution, you get a position. But this is uncertain to plus or minus 5 to 6 meters. It's very large uncertainty. But supposing I have a receiver, another similar receiver nearby, and that also receives the signal from these satellites and determines its position. Now, because these two receivers are not too far away from each other, the ionosphere, the troposphere, the satellites, clocks, orbits, etc., all happen almost identically for both the receivers. And in the technical jargon, what we call them as common mode errors. So the errors in the position determination for these two receivers, which are nearby and not too far away from each other, are all common mode. Our errors are almost identical in these two receivers. Now, supposing one of the two receivers is a base receiver, and whose position is already known accurately, and it determines its position using the satellite navigation. So it can calculate how much is the error in the position, because it knows the real position already by some other means. So that error, if you have a radio link and transmit in real time to the other receiver, it can incorporate that error and improve the position of this. So this is the very simple principle of what is known as differential GNSS or differential GPS. And if I do this in real time, this is called real-time kinematics or RTK. So RTK receiver basically consists of a base station and another and typical user, which can take his receiver anywhere in the vicinity and use this radio link to receive the error in the correction to be given in the position in real time. So it can determine its position very, very accurately. And by this technique, you can get position uncertainties which are only a few centimeters or certainly better than 1 meter. Now, there are lots of applications for such precise position determination using real-time kinematics, RTK. So there are a lot of applications, but I'm not going to go into all those details. But just to show you an interesting application, all of you are familiar with the drone show. It's so interesting, so lovely. On the Republic Day, on the Beating the Retreat, we get these drone shows, and on many other occasions. That's fantastic things. So these drones are these objects, and there are literally thousands of them, which are flown, and underneath each drone is a light. So when they all fly in a certain formation, it produces a very nice pattern. Now, remember, this formation is possible only if these drones, the relative position of all the few thousand drones are known, very, very known and controlled and moved very, very precisely. And you know how that is done? That is done using RTK. That is done using differential GNSS.
Look to the skies as we embark on a journey to explore the limitless possibilities of the future. Let us follow along with the early biplane as it recreates the pivotal moment in.
I just stopped here. See, each dot here is one drone. And typically the distance between the drone is about a meter or so, less than a meter, sometimes a little more than a meter. And the entire thing is forming a very nice, stable platform. Sorry, I think I should let you see this.
Look to the skies as we embark on a journey to explore the limitless possibilities of the future. Let us follow along with the early biplane as it recreates the pivotal moment in Indian civil aviation. This is the plane that carried 6,000 letters from Allahabad to Delhi in present-day Uttar Pradesh, becoming the world's first recorded airmail.
Okay, so this is how this is done, right? So finally, we are not going to discuss all this, but the GPS or the Global Navigation Satellite System has a large number of applications, civilian applications in road navigation, transportation systems, in rail navigation, air navigation, maritime navigation, etc. It also has defense applications, very strategic applications for missile guidance, gun, mortar, launcher, etc., and lots of things. So finally, to summarize, so in this lecture, we have talked about the basic principle underlying the satellite navigation, the range navigation. We have given some idea of details of the entire system of global navigation satellite systems. I've just told you very briefly what are the error sources and how they result in position uncertainties. I've told you very briefly differential navigation concept by which you can improve the positioning accuracy to within a few centimeters or at least within less than a meter. And then we have just quickly brushed through some applications. So that's it. And what next? What are we working on now? Around the Earth, large number of global navigation satellite systems are already working. We are trying to improve them, but they're more or less operational. So what are we working on now? We are actually working on similar satellite navigation systems on the moon and beyond in the other planets. Because see, very soon we are going to embark on missions to planets, Mars, Jupiter, and so on. It'll probably not happen in my lifetime, but it'll happen sometime. Perhaps some of you younger people will get to see actually men landing on Mars and moon, Jupiter and so on and so forth. And moon is one of the intermediate stations from where we can launch these planetary missions. Now, in order for us to settle on the moon, we must have a robust navigation system on the moon. Right now, it's all very uncertain. You land somewhere in the polar region, you land somewhere on the backside of the moon and so on. But you must have a robust, internationally accepted navigation system. So we are actually trying to work on a satellite navigation system which is applicable for the moon. So that's that by the time some of you grow up and become, if you pursue a career in science, you will probably be working on such systems. Okay. So and right now these scientific discussions are very current and they're very hot discussions. One was carried out just last February. This is one of the important meetings. So that's it. Thank you very much for your kind attention, and I'll be happy to take some questions.
Thank you so much, sir. Thank you so much. This was an absolutely amazing session. What a treat to watch. I loved it. I hope everybody else loved it too. So we'll take some questions. We'll keep it shorter because there is a time constraint. People who wish to ask their questions may raise their hands. We'll help them open their mic and open their camera, and they can ask their questions directly to sir. All right. You may raise your hands, and we'll take questions from there. Anand,
cannot unmute due to network issues. So maybe you write on the chat box and okay, somebody is there.
Yeah.
Hello, sir, and thank you for a wonderful session. I loved it. I just had a very simple doubt. In one of your slides, sir, you mentioned about all these the bunch satellites and all of them having the same inclination, like in one of the slides, 56 degrees.
They all have same inclination, but see, just try and visualize the Earth, and it's rotating about its axis. So you can have one orbital plane like this. You can have another orbital plane like this, yet another one. So all of them are inclined to the equator at the same angle, but they're displaced in the equatorial direction. They're different orbital planes, but each plane has an angle which is 55 degrees to the equator.
Each plane has an angle that is...
The satellite orbit, try to visualize this in 3 dimensions, right? This is the Earth, and I have a plane which is inclined to the equator at 55 degrees, right? In this direction. I can have this plane point this way. It's still inclined at 55 degrees, but in a different direction.
Right. So whenever you're talking about bunch satellites and its inclination degree, you're talking about its inclination to the equator.
That's right.
Yeah.
That's right.
Thank you. Thanks a lot.
Sure.
Thanks, Anand. We'll take Atharva's question now. Atharva, you may open your mic. Dr. Shah.
So, first of all, thank you, sir, for this energetic session. Sir, I have a simple doubt that is it possible that the broadcaster signals given by the satellite in space, in any case, taken by other countries' tracking station or stations?
Well, they can surely. Why not? But then it doesn't really serve any purpose, because firstly, just one single station tracking a satellite makes no difference. You must have a network, because unless you have a network, you cannot determine the orbit of the satellite, for example. But to answer your question, that the tracking, there's a lot of international cooperation in this activity. You know, there are stations which are known as IGS station, International GNSS System. So IGS is an international body which has put its tracking station all over the globe. And many of the agencies, such as our ISRO, takes help from the IGS to receive their tracking data to improve the orbits of our own satellites. You know, so that's the way in which international tracking can help.
So, sir, I think there's a national cooperation there between the countries.
Yes, there is.
Thank you, Athar. We'll take Avjeet's question. Avjeet, you may open your mic or hand your camera and you can speak. Avjeet, are you there? Seems like...
So before we wrap up, I have just a final question. We all know GPS and other global systems dominate worldwide navigation today, but India has its own NAVIC system. How do you see, and we can see our NAVIC evolving in the future, and what role can it play compared to global systems like GPS?
Well, see, NAVIC, first of all, is not a global system. It's only regional. It covers India and surroundings, right? So,
yes, sir.
It can never replace GPS or GLONASS or Galileo. But just for your information, you know, ISRO is actually planning to develop a global navigation system, which will probably happen in the next 5 or 10 years from now. So it's very much in the work. That is one. The other thing is a typical mobile phone that you have, a smartphone that you have. Today, it has a satellite navigation receiver, which is able to receive signals not from just one constellation, but from all other constellations. You know, GPS, Galileo, GLONASS, Beidou, etc. So it can do calculations based on all these pseudo-range measurements. Right?
Yes, sir.
Okay.
We will take next Rinku Das.
Yes.
Yes, ma'am, you can go ahead.
The position can be determined by the local transmitter or the satellite. So how can we understand how my position is determined, whether it is local transmitter or whether it is satellite?
No. Local transmitter example was just to tell you the principle of how it works. In real life, there are no local transmitters which are transmitting time signal. That example that I gave right in the beginning was just to make you understand how a range navigation works. In real life, you have signals only coming from the satellites, no local transmitters. That local transmitter was just an illustration. Okay?
Okay, then all type of signals comes from the satellite in our mobile.
Only satellites, no local transmitters.
Okay, and there must be 3 signals coming from 3 different directions of
not just 3. There are
the satellite, so that our position can be
exactly not 3. There are, the minimum required is 4 signals from 4 satellites, because you must solve for 4 unknowns. So you need at least 4 measurements. So, but in real life, actually you get about 30-40 satellites from any place on the Earth, right? It's an overdetermined solution. You have a simultaneous equation in which you have 4 unknowns, but
It's very
many
complex
parameters.
that signals simultaneously 30 to 40 signals is coming in our mobile and
Yes. Yes.
Okay,
Yes.
okay. Thank you, sir.
Thank you. We'll take Yashwant's question. Yashwant, you may go ahead.
Thank you so for the opportunity. So my question to you is that there are, like we know, there are some small amount of errors for precise calculations. So what are the measures we should take to minimize the chance of error?
Oh, well, actually for the kind of errors that I showed to you, like there are errors because of satellite position uncertainty. There are errors because of satellite clock uncertainty. There are errors because of the delay through the ionosphere. You cannot take any precautions to avoid these errors. They are not in your control, see? The ionosphere is the ionosphere. So how can you control the ionosphere? So these errors are not in your control.
Like any external calculations, like we also included the delay from ionosphere to have a perfect calculation. Like, are there any such mathematical things to be taken?
In the receiver, the ionospheric delay is computed using a model and then subtracted from the measurement. But the model can never replace the real ionosphere. The model has a lot of variability, a lot of uncertainty. So that's why it still has some residual error. You can reduce it, but you cannot eliminate it completely. Right?
Like for something like very precise measurement for missile launches, etc., how we take such precise measurements?
Oh, yeah. For precise measurements, you use differential GNSS. For very precise measurements, you have to use differential GNSS, the RTK that I told you. Of course, there are many more details. In a short talk like this, I cannot naturally cover all those intricate details. There are techniques by which you can reduce the position uncertainty, but basically they follow the principles that I described, namely the differential corrections. Right?
Okay, thank you, sir.
Thank you, Yashwant.
Sorry, I just had 2 questions extending to it. Can I ask?
Yeah, sure.
Sir, about remitting those inaccuracies, those errors, can we not use something else that is up in the atmosphere and recording the calculations? Maybe flying airplanes, maybe I take a brim up and...
Yes. Only, Anand, the problem is you can fly aircrafts and so on and so forth, but these errors are coming from, remember, I said the ionosphere is about 250 kilometers. You cannot fly an aircraft 250 kilometers high.
Right. No, forget about the ionosphere, but at least whatever is in our control, we can record accurate measurements, at least from those flying instruments. And also the second question I wanted to add in is about the differential thing you mentioned, that we can have a base somewhere and then the local...
Yeah. That is a very common practice.
Right. So in fact, the base can move. Like if the airplane is a base, then it can move and then you can have a varying precise measurement.
No, Anand, actually there are ways in which you can have this differential correction over very large distances. Those are details that I naturally didn't want to, which I couldn't describe in such a short talk. There are some systems which are called augmentation of the satellite. What happens is you can have not one base station, but a few base stations, hence covering a very large area.
Right.
You can take all the corrections take all the corrections and compile them and transmit them to a satellite which is fixed, and it re-radiates the correction, so it covers a very large area.
Right. And it
So-
will get much more precise.
Then you can have this differential correction not over a few tens of kilometers. You can have the differential correction over, let's say, the whole of India. So
Right.
such a system is called an augmented GNSS. The one example is called Gagan. Gagan is I forget the acronym. It's something that works similar to what I just described.
Right.
Right.
Yeah. The more you speak,
Over
the more
a
we
very
feel
large
like,
area, over the
running into
entire
this.
Indian subcontinent. Yes.
Yeah, we really wish this lecture had been much more longer. So it's really, really awesome. And so before I go, I do wish that you live very, very long life, long enough to see we settle satellites on other moon and Jupiter, Mars, etc.
Thank you.
Thank you, Anand. Best wishes.
All right.
But yeah.
Good evening, sir.
Yeah, Nirmal, yes.
Actually, sir, this is Nirmal Ram.
Yeah, please.
Actually, sir, from your opinion, what kind of satellite does India need for its future, sir?
Oh, are you referring specifically to satellite navigation? Because the satellites are used for navigation, they're used for remote sensing, they're used for communication, a variety of applications.
Especially for defense.
For defense. Oh, for
Yes,
defense, there are surveillance satellites, there are remote sensing satellites, all kinds of things. But usually in an open forum like this, one does not talk about defense applications. So, I mean, there are Indian defense satellites, there are missions, but in an open forum like this, it's difficult to describe what they do. You know.
And one more question, sir.
Yeah.
Sir, can
Yes.
you hear me?
Yeah, I can hear
Sir.
you. Please go ahead.
Yes, sir. What kind of startups can be found from satellite navigation, sir? Is there any possible startups?
Fantastic question. Thank you very much for bringing this up. How old are you?
Actually, I'm 17, sir.
Okay, well, you are a little bit on the lower side, but I am actually interacting with, one would by listening to the description that I just gave you, you'd probably think that making such a satellite navigation system would require a big agency like ISRO or NASA or EU and so on. But it turns out that there are some startups actually in India. I'm interacting with a couple of boys who are pass out from IIT Madras, and they have just got funded for their startup. It's called Vyomic, and they have promised a satellite navigation system using LEO satellites in about 2 years from now. So there are startups, not with experienced elderly people, but young pass out from IIT Madras, a couple of guys. They and a few others are actually working on developing a complete satellite navigation system using LEO satellites. Maybe in another few years, you will hear their success story. So we are working on it.
Sure, sir, sure. Thanks for your valuable words, sir.
Thank you, Nirmal. We'll take one last question. Let's take Jivantika's question. Please go ahead, Jivantika.
Hello, sir. Good
Hello.
evening. Sir, being an user who we are just collecting data, we are not part of ISRO. Can we track the position of the satellite? Just example, the NISR is launched. Can we track where the NISR is exactly today?
Well, you cannot track the position of NISR because that's not firstly a navigation satellite. I mean, not with the the navigation receiver. You probably have with you a GPS receiver, right? Or a multi-constellation satellite receiver. I'm not sure you can track the NICER's position with this receiver, because NICER as such will not transmit in these satellite navigation bands. So you'll have to talk to somebody in ISRO to figure out how you can track NICER. Maybe it transmits some information on its orbit.
Okay, sir. Thank you, sir.
Thank you.
Thank you, Jivantika, for your question. Thank you so much, sir. It's been an absolutely treat to watch all the questions and the session. It has been absolutely awesome. I hope everybody liked it. If you liked it, please let us know. All right. Thank you so much, sir, for coming here, for giving us your time.
My
We are
pleasure.
extremely grateful to you.
Thank you, sir. Thank you so much. Yash, I would just like to mention that he is one of the pioneers in the atomic watch, atomic clock making. He is one of the person who told us in a session where what a quartz clock looks like and how does atomic clock actually works. So that was really interesting, really, really interesting. I would definitely recommend you to get a session on atomic clocks in future with him, definitely.
Yes, ma'am, sure will. Thank you so much, sir. Thank you so much, sir. It's been a treat. My words are less, but it's been an awesome session. Thank you, everybody. A few last instructions for you all. I would like to say, for people who are joining in, you will have to fill a Google form where you'll have to attach your images and your email for us to provide you with certificates. We will send you the Google forms very, very shortly. We will also help you send you the next schedules of the session, because this will take for 7 days. And for people who are interested in winter school or more interested in diving into a lot of cosmos and stuff, they can check out the website. All the syllabus and stuff is posted right there. And if you have any queries left for people who have typed their stuff in chats, you can mail us directly to propagation.connect@gmail.com. We'll take your questions. We'll answer them well. And see you in the next session. Thank you so much, sir, again. We'll end the calls here. We are extremely grateful for everybody to come here. And we'll see you in the next session. Thank you so much, sir.
Thank you.
Thank you, sir. Thank you.
Bye-bye.
Thank you, sir.
Good night.
Good night, everybody. Good night.
Good night, sir.
Thank you so much, sir.
One last thing, people, can you switch on your cameras so we can take a quick picture with everybody? I will take a quick picture. Just give me a second. Just view.